Well, it seems like a long time ago when we were talking about section 5.1, and we had just started it, but it was a good idea to get a little bit of this out of the way since we do have to spend 3 days on section 5.1. So our objectives were to classify polynomials and to graph polynomial functions and describe end behavior. But we really only got to the classifying polynomials part. We started to get a feel for, okay, what power, what degree of polynomial should I use for any situation that I have. And that's what this getting ready was about, was trying to figure out, what degree are we going to need here to make this work. So we went through all of these wonderful little pieces about our polynomial functions, and then we talked through this chart that gave us the names. Now, naming is called classifying. And so what they're going to do is they're going to say classify by degree, classify by number of terms. And we had this little chart that helped us through all of those names. And I would say it's very, very typical that people remember monomial, binomial, trinomial, polynomial, 4 terms, etc. That one just seems very intuitive given that we talk about that all the way through Algebra 2. But sometimes it takes people a little while to get used to this. 0 degree is a constant, 1st degree is linear, 2nd is quadratic, 3rd is cubic, 4th is quartic, and 5 is quintic. So make sure that you're taking another look at those so that you have at least the degree down to 5 in your memory. And like I said, that's what we'll be testing you on. That would probably be the maximum we would give you anyway, would be a degree 5 polynomial. But hopefully these as well, you're thinking linear. I think we've talked about that before because that's when we were graphing lines, which was x to the first. And then degree 2 polynomial, a quadratic. Yeah, we've graphed a lot of quadratics and talked about those. These others, you get this feeling like there's got to be something that we're supposed to know about this, because they're telling us about the names, and we go through and talk about which polynomials should we represent with what degree. And again, all of this was before the break. And we found out as long as we check and make sure that all of the x values are going up by the same interval, and this time they're going up by 1s, then all we have to do is use subtraction to see what's going on and which degree we should use. So we were using subtraction, and if after the first set of subtractions all of these numbers came out to be exactly the same, it was called a first degree difference, and we could use a first degree, a linear equation to represent that. But if it took 2 sets of subtractions, then it was a second degree, and that was going to be a quadratic, etc. So that was what we did before the break. Now today we need to really focus on the second piece to that objective that we had, which was graph polynomial functions and describe their end behavior. Now that one, hopefully you're thinking, so every polynomial, like ever? And the answer is yes. We want to be able to have an idea of what a polynomial looks like just by looking at what is the degree of this polynomial? What's the leading coefficient? What do the numbers and the letters tell us? So the degree of a polynomial function affects the shape of the graph, and it determines the maximum number of what are called turning points, or places where the graph changes direction. So the degree, the highest power of any of the variables that we have in our graph equation, is going to tell us something about the graph. And like it says, it's going to tell us also, but with a little bit of math, not much, the number of turning points. So turning points are when the graph was going up and all of a sudden it started to come down. So the graph from left to right, because that's how we read graphs, was going up, but then it started to go down. That's a turning point. Or it could be a graph that was going down and all of a sudden started to go up. So this one, I'm just going to call it the TPs, would actually have two of them. It was going down and then started to go up. And it was going up and then it started to go back down. So what they're saying here is just by knowing, hey, I put this in standard form, I can find the highest power of the variable. That's going to tell me something about how many turning points this graph is going to have. It also affects what's called the end behavior, or the directions of the graph to the far left and to the far right. So end behavior describes what happens if, and now I'm going to put myself right in the middle here, and let's just say I'm standing below the number line and 0 right above my head here. As we go to the left forever, what is the graph doing? Is it going up or is it going down? As we go to the right forever, what is the graph doing? Is the graph going up or is it going down? That's called the end behavior. And I'm going to show you two ways that we write that. This year, we're going to limit it to, hey, up or down. But next year, if you're taking college algebra or pre-calculus, I want you to see that we write this using a little bit of calculus notation, and it's called limit notation. For polynomial functions, there are 4 types of end behavior, which again, that's our objective today, talking about that end behavior. 4 types of end behavior as you move to the left and move to the right away from the origin. Could be up and up, could be down and up, could be down and down, could be up and down. So there's 4 different things that could happen here. And here are 4 situations where we're going to see this end behavior. Now the end behavior is the behavior that the arrows are telling us is going to happen. So as I look at this graph, I see, all right, as this is going to the left forever over here, this is going up. And as I go to the right forever, it's also going up. So this one is up and up. The second one, the arrows are showing me as I go to the left forever, it's going down. And as I go to the right forever, it's going down. But then we start to see where things change. And that's going to be in this third graph, because as we go to the left forever, this graph is going down. But if we start kind of think of it as the middle of the graph and we go to the right forever, now it's going up. So those arrows are showing us down and up. And then in the last one, as we go to the left forever, this is going up. And as we go to the right forever, it's going down. So this page said, really with the degree, we're supposed to be able to know what's going to happen as we look at this end behavior. And I see this one was an x to the 4th and this one was an x squared. These two had x cubes. Now the first two, if you just look at the end behavior and you ignore the turning points in there, they look a lot like parabolas. But these last two, they look more like, oh, I don't know, kind of a snake-like curve. We call it a snake-like curve, or an S-curve is what we get for those cubics. Now, we are going to, on our test and everything else that we ask you for in here, we're going to say up and up, down and down, down and up and down. But next year, when you get to college algebra and pre-calculus, this is written differently. It uses this notation as x approaches negative infinity, f of x approaches what? And as x approaches positive infinity, f of x approaches what? So what we're doing here is showing you what you're going to use next year, but testing you on just knowing up and up, down and down, down and up and down. Because this is going to help you out next year. The more you're exposed to something, then the easier it's going to be for you to learn it. So this is how it's written. The limit as x approaches negative infinity of f of x equals. Now our job, after we write all that notation down, is just to fill in that little blank. We look at this and say as x approaches negative infinity. So here I am at the number line again, smack dab in the middle. And that means I've got to be going to the left forever, because that's where negative infinity is. Well, this graph, as I go to the left forever, is going up, and that's going to be infinity. Now, we used to write it positive infinity, but over the years, mathematicians said, well, that's kind of ridiculous because infinity is positive, you know. But for this portion, we're going up, which is infinity. Then, the limit as x approaches infinity, or positive infinity in some of the older books, for f of x equals. And so, again, looking at this first graph, well, as I go to the left, it's going up forever. But as I go to the right, which is what we would be doing if we're approaching positive infinity, it's also going up. So this would also be infinity. So like I said, I just want to expose you to that notation so that you can see, oh yeah, next year when you start talking about this end behavior and you're seeing this limit notation, yeah, I remember we saw that. So in a couple of different places as we go through this, I'll be writing our limit notation as we would in college algebra or in pre-calculus just to get you prepared for that. Now, our objective is all about understanding how the degree tells us what's going to happen with the end behavior. And it turns out it's not just the degree. There's another piece to this. And that's going to be because the end behavior of a polynomial function can be determined from the leading term, a, x to the n, when the polynomial is in standard form. End behavior of a polynomial function of degree n with the leading term of ax to the n, and like it says, moving away from the origin. So, if we have an even degree, 2, 4, 6, 8, 10, etc., and the number that's in front of our variable, that's going to be our leading coefficient, is positive, in fact, let me put LC right up here for you, then it's going to be up and up. So it's going to look like a little parabola. Now, that doesn't mean that there's no turning points here. There probably will be turning points, but we're just going to go ahead and talk about the end behavior. So the end behavior is the arrows. The stuff that happens in the middle, we'll still probably be using a graphing calculator to get a lot of that information. But if the leading coefficient is positive and the degree is even, it's going to be up and up. If it's even, but there's a negative in front of it, well, we knew this from our parabolas before. Then it's going to open down. Again, could be some turning points in here. We're not concerned with those. We just want to know what is the end behavior doing. And this is down and down. Now, we're getting to the ones that we haven't had as much experience with, and that's going to be, what if the degree is odd? So what if it's a cubic, 5th power, 7th power? What do those look like? Well, if A is positive, they're going to start low and go high. So it'll be down and up. If A is negative, that flips around. So it will be up and down. So we have 4 little pieces here that, yes, we do usually just memorize. The up and up, down and down piece there. We memorize what is in the table here, which is what's the degree, and then positive or negative leading coefficient. So here's what this does. It summarizes what we had in the little chart. All even degree functions behave as parabolics. So that means overall their end behavior is going to be like a parabola. Doesn't mean that the stuff in the middle is going to look like a parabola. It means at the ends it'll look parabolic. And all odd degree functions behave as S-curves or snake-like curves. So let's go ahead and write this down in just kind of a summary form, so when you go to your homework you can look at this and say, oh yeah, this makes sense. So we have 2 of these that are going to have an even degree, 2, 4, 6, 8, etc. If it has a positive leading coefficient, the end behavior is going to be up and up. It's just going to look like a big parabola opening up. Again, ignore the middle piece. So I'll erase that. Ignore what happens inside there. That's not what we're interested in. End behavior is what's happening at the arrows. So could have some up and down stuff going on in here. But the end behavior will be up and up. If we have a negative leading coefficient, well, that's going to turn that parabola upside down. And it'll be down and down. If we have an odd degree, we have two different looks. If it has a positive leading coefficient, it starts low and it goes high, which kind of makes sense to me, you know, that the first one would be low to high. That just makes sense. And then when you do a negative leading coefficient, that reverses it. So it's an S-like curve. And again, there could be lots of strange things happening in the middle. The middle is not what we're talking about right now. We're talking about the end behavior. What's happening with those arrows? Are they going up or are they going down? And the one on the left is going down and the one on the right is going up. So right now, we're not talking about what's happening in the middle of the graph. We're talking about the end behaviors. So problem 2 says describing end behavior of polynomial functions. Consider the leading term of each polynomial function. What is the end behavior of the graph? And then check your answer with the graphing calculator. And I can see my blue is not showing up. There we go. Oh, way too blue. Let's do this. Always something. This morning, the projector wouldn't turn on. And I was in on Saturday and I'd used it and didn't have any trouble at all. So that was going to be something. Consider the leading term of each polynomial function. What is the end behavior of the graph? And then check your answer with the graphing calculator. All right, so I'm looking at A. And I first want to put it in standard form if it's not already there. But this one is. We've got x to the third. There's no x squared, and then it's x to the first, so it is in descending order. So I think, all right, this is a degree that's odd. Now, is there a positive or a negative number in front of it? And there's a positive 4. So it has a positive leading coefficient. So without doing any graphing, that means it should have down and up. That should be the end behavior. But after we get above talking about quadratics, which are x squareds, after that, we usually use the graphing calculator to graph these because they start to get pretty involved. So what we're going to do is we're going to plop this in the calculator and we're going to actually get some of the numbers that need to go in here. So we have y equals, this one was 4x to the third minus 3x. 4x to the third, and then I have to pop that out of that exponent there, minus 3x. And I want to see the graph. Zoom 6. Now, that end behavior is exactly what I expected to happen. Down and up. Because this is where the arrows would go if our graphing calculator allowed us to put arrows on there. So down and up. Now, we have to transfer that onto the graph. So that means we need some points. And that's going to be second graph. And I'd want to stick with things that are definitely going to be graphable on my negative 10 to 10. But what we would want to do is write down everything between. We could put negative 2, negative 26 in our table. That'll at least give us something to aim at. Negative 1, 0, 0, 1, 1, 226. We'll write those down. So that was -2, -26, -1, -1, 0, 0, 1, 1, and then 226. And again, we're not going to try and graph the -26 or the 226, but we're going to go ahead and aim at those points. So we had -1, -1, 0, 0, 1, 1, and then we had to big time aim downward. We want to make sure it looks like it's going to go down a ways before we can get to that -26, and then upward really fast. But you'll notice I didn't draw in the rest of this, and that's because there were some turning points there, and those are important points. So when I look at this graph, I would definitely want to know where is this and where is this, so that I can get those accurately on my graph. And that's the local max and the local min, which we actually cover in another section, but I'm going to show it to you now so that you'll have double coverage by the time we get to taking a test on this. Remember, Blinky can find a lot of stuff for us. So if we do second trace, notice 3 is minimum and 4 is maximum, and those are both things I need. So I'm going to do number 4 first because we read graphs from left to right, so I usually do the left one first. Now Blinky's asking us down here, are you on the left side of that little hill? Well, here's the little hill, and no, I'm not on the left side yet. So I'm going to use my left arrow to get to the left side of that hill, and it doesn't matter where on the left side, just somewhere over there, and hit enter. Well then, Blinky says, now are you on the right side of the hill? Silly question, Blinky, you know I was just on the left side. So now I use my right arrow to make sure that I'm starting to go down on the right side of the hill, and press enter. And then Blinky gets playful and says, do you want to take a guess? No, Blinky, I'm not going to take a guess. That's why I'm using you. So hit enter again. And there it is. And it's really, really close to 0.51. That is called a local maximum at 0.51. And I'm going to get that on there. So I think there was a negative in there. Negative in front. I was just thinking that doesn't make any sense without the negative. So negative 0.51. Now I know this part of the graph. But there was also a little valley. So I have to figure out, where is this little valley over here? Well, again, that was under minimum. Second trace, number 3. And Blinky's asking me, are you on the left side of the valley? You'll notice I just moved Blinky a little bit closer, because the closer you are without actually being at the bottom, the less math Blinky has to do, because Blinky's actually doing calculus when we hit that enter button for this one. So somewhere over there, enter, and then right arrow until you're coming up out of the valley on the right-hand side, enter, enter through guess. That one is really close to 0.5, -1. Notice this would round here to 0.5. So that is our local minimum. I'm going to try and stick with the red here. So that gets me a really accurate graph. And again, if they just wanted the end behavior, I had that before I even started because I knew it was an odd degree with a positive leading coefficient. So the graph part, that's just extra nice. We get all that good stuff on there. Well, let's go to B. B says y equals negative 2x to the fourth plus 8x to the third minus 8x squared plus 2. And I notice, hey, this one is in standard form already. That was awfully nice of them. And it's a degree 4, so it's an even degree. But it has a negative 2 in front of it. So it has a negative leading coefficient. So I remember all the evens look like parabolas, but if it's got a negative in front, well, then it's going to go down and down. So now, the rest of it, I need to plop it into the calculator to take a peek. Now, how do I know what's going to happen? Well, here's what I know. I know there's going to be an arrow going down and an arrow going down. The stuff in the middle, I don't know. All of that is determined by these other terms that are behind it. So like I said, at this point we usually say, grab a graphing calculator, punch it in, because we're above the degree 2 polynomial. So y equals, clear that one out. And this one was negative 2x to the fourth. And I've got to pop it out of that exponent position. And then we've got plus 8x to the third. Pop it out of the exponent position. Minus 8x squared plus 2. Now again, we know what the end behavior is going to look like, but let's see the rest of it. There it is, little upside down looking parabola right there. And we can definitely see the down and down where the arrows would be. We just have to get the rest of it on there. So that means we're going to go into the table feature and find some points. I probably would write down the negative 1, negative 16, 0, 2, 1, 0, 2, 2, and 3, negative 16. But the rest of them are getting very, very far away from our little negative 10 to 10 window. And not a lot of space here. I think I will make my table up here. So we had negative 1, negative 16, 0, 2, 1, 0, 2, 2, and 3, negative 16. So what we want to be careful about is making sure that we show that down and down without, lost my little bar, there it is, without having it hit a number before it gets to that negative 16. We know it's supposed to keep going down pretty steep. So we have 0, 2, 1, 0, 2, 2, and then this was going almost straight, whoops, don't want to make it look like a curve. Straight down, almost straight down. But the problem is that I don't know is this 0, 2, the very top of the hill. Is this 1, 0, the very bottom of the valley? How about over here? That's another top of the hill. Is that going to be at 2, 2? And since I don't know that that's exactly perfect, that's what I would use Blinky for, would be to figure out where are these. So back to the graph. I have 2 local maximums that I have to find. And local just means within a certain region. You know, we know this has some top points and that it has a lower point in it, and that's what we have to find. So, second, trace number 4, and I'm on the left side of the hill, so I press enter. Use my arrow to go to the right side of the hill, press enter, and enter through guess. Now, this is what I was hoping we would see. People get to this point and they're like, oh my gosh, it wasn't the top of the hill because this says 2.92. No, it doesn't. It says 2.9212 e to the negative 6. Now that's scientific notation. So it's telling us we have to move this little decimal place 6 places to the left. That's 0 to us. That will round to 0. This is actually the calculator kind of apologizing and saying, I couldn't get you perfectly 0, but you know, it's really close. And yes, that's 0 for us. I mean, even if we're going to 3 decimal places, that's going to be 0. So 0.2 was our local max. Now let's check that local min in the middle. Second trace, number 3. I'm on the left side of the valley, so I hit enter. Go to the right side of the valley, hit enter, and enter through guess. Again, we see some scientific notation. But when it's times 10 to the negative 11th, wow, we're going to have point, and then we'll have 0 10 times before we'll write 106. So that's definitely 0. So this would round to 10, which is what we already had on our graph. Now let's check on the other one. Second trace, number 4, left side, right side, enter. And this one is, again, super close to 2.2. So those points that we already had on there before did end up being our local mins and our local maxes. But the end behavior, we didn't even really need to graph it to get that, to know that it was going to be down and down. It's nice to do it, you know, to verify that, but we didn't need that piece. So for this last one down here, for got it 2, it says consider the leading term of y equals negative 4x to the third plus 2x squared plus 7. What is the end behavior of the graph? I don't even want you to graph this. What I want you to do is I'm going to put you in your little breakout sessions, and I want you to talk about how do you know that this is up and up, down and down, up and down, down and up. And that's what we're going to find, is just that information. So you'll be in a little breakout group, and I won't make them very large here, if my computer will behave itself. Again, talk about what you see and what it tells you when you get to the breakout rooms. So make sure you unmute yourselves. Somebody unmute and take charge so you guys can all get talking about it. What you want to do is be able to explain, is it up and up, down and down, up and down, down and up, and then how would you know that from the information? Did you already do this one, everybody? Somebody's going to have to unmute and take charge here. So talk about what you're looking for and how you knew if it was up and up, down and down, all of that good stuff. Somebody be brave and unmute, and maybe you already talked about it all, but how did you know up and up, down and down, all of that? All right, so it looks like we're getting people back now. And I need somebody to unmute and be brave and tell me if they had up and up, down and down, up and down, or down and up. Up and down. Give everybody a second to look at that and think about whether that makes sense with what you were talking about. I hope some of the groups got to talking. The ones I peeked in on weren't talking yet. So this one is already in standard form. It's degree 3, which is odd. And it has a negative leading coefficient. Yeah, that's what they do. They are up and down. Now, we could pop it in the graphing calculator, but again, all we needed was the end behavior. By the time we get to the test, we want to be able to do all of that. And then I want to remind everybody that this will look a little different when you get to next year's classes, because we'll say the limit as x approaches negative infinity for f of x equals blank, and the limit as x approaches infinity for f of x equals blank. But this just says exactly what we just saw. If you're going to the left forever, that's negative infinity, where's the graph going? Well, it's going up. As we go to the right forever, well, the graph is going down, and that's where x approaches infinity. So that would be a negative infinity. So again, in a normal year, we would have you doing this limit notation in Algebra 2. But this year, because things are not normal, we're definitely going to stick with up and down. All right, so what about all those little lumpy bumpy spots, those turning points? Should we have any idea how many of those are supposed to happen? And it turns out, yes, again, by the degree, we can tell that. So in general, the graph of a polynomial function of degree n, where n is greater than or equal to 1, so it's at least a line, it has at most n minus 1 turning points. So if it's a degree 4 polynomial, they're saying if you take 1 away from that, it could have as many as 3 turning points. It doesn't have to. It might just have 1. But at most, it will have 3. And it says the graph of a polynomial function of odd degree always has an even number of turning points. And you think, well, duh, because, you know, if it's an odd degree polynomial, let's say it's 7, so a degree 7, well, then you take 7 minus 1 and you get 6. And no matter what odd number you pick, if you subtract 1, you're going to get an even number. Yeah, but remember, this is at most. So a degree 7 polynomial might have at most 6 turning points. It might just have 2, 4. Never know. So that's why we use the graphing calculator to tell us about the turning points. The graph of a polynomial function of even degree, for the same reason, we'll have an odd number of turning points. So this one, it's a line. It doesn't have any turning points. As you go from left to right, it was always going up. So 0 turning points. This is a degree 2. It has 1 turning point. 2 minus 1 is 1. And there it is. These are both degree 3. But this one doesn't have any turning points. It is just going up from left to right. While this one has 2 of them. Right there. So 3 minus 1 is 2. Doesn't that mean that they all have to have 2 turning points? No, it said at most 2 turning points. So it might not have any. It might have 2. And how we're going to find that out is by just putting them in the graphing calculator and counting. How many turning points do they have? So I think this is a good place to stop, because we'll finish up the rest of this with some more of these problems involving, talking about degree, up and up, down and down. And we're also going to do a little bit more of the local max, local min stuff tomorrow. So we'll leave problem 3, and it's got it for tomorrow. For the homework for today, you'll do those. So definitely we've got a really good start on our objective. In fact, I'm certain that probably most of you're like, I already have this end behavior stuff down. I already know what I'm doing here. But we're going to do another day, because we really do have to memorize the up and up, down and down up and down behaviors. Remember that for the turning points, you're going to have to actually graph that. If you don't have your own graphing calculator, keep in mind in Rapid Identity, we have that TI-84 Plus app. But that'll finish it off for today.